Hello everyone, the title of my paper is Scaling Up the IFDS Algorithm with Efficient Disk-Assisted Computing. Firstly, I will introduce the background of my paper. The IFDS analysis framework solves inter-procedural, context-sensitive, and flow-sensitive analysis of finite distributed subset problems. IFDS problems can be transformed into a special kind of graph reachability problem. The IFDS analysis framework has been implemented in various analysis and compilation frameworks such as VALA, SUIT, and LLVM. Meantime, it can be used to solve a wide range of problems, such as pointer analysis, tent analysis, slicing analysis, bug detection, shape analysis, and so on. Although IFDS framework can improve scalability by defining a special data flow problem, it still is a memory-intensive algorithm. The space complexity is the big O of ED square. The E is edges in the graph, and the D represents a set of data flow facts. It can be compute and memory intensive when the program size or the domain of data flow facts is large. According to a previous research, there are 16 Android apps are unanalyzable on a computer server with 730 GB of RAM. According to the extended algorithm of IFDS, path edge records the set of path edges, representing a subset of the same level realizable paths. Incoming records the set of data flow facts generated at entry node of a procedure and their predecessors. And summary records the set of path edges from entry node to exit node of a procedure. Next, I will introduce IFDS algorithm by a simple example. The demo display FlowDroid, a state-of-the-art IFDS-based tent analysis tool, calculates graph reachability paths step by step. The gray box is the code. Here, 0 signifies an empty set of facts, such as new data flow facts can be generated at a program point. We assume that the source function is a sensitive API, so a data flow fact A is generated at line 2. The solid edge from 0 to data flow fact A represents this step. Meanwhile, a path edge from 0 at line 1 to data flow fact A at line 2 is added into the set of path edge. Here we use dotted edge represented, and we give it a unique ID 1. There is a call fight at line 3. Value A is an actual parameter. X is a formal parameter. Data flow factor X is generated because of the invoke at line 3. The path edge from data flow fact X at line 8 to X at line 8 is added into memory. And the data flow fact X and the predecessor H1 is added into incoming set. Data flow fact Y and the path edge 3 is generated because of a sign statement at line 9. At the exit node at line 10, path edge 4 is added into path edge set and end summary set. According the incoming set, we find the return site and generate path edge 5. Finally, data flow fact B enters sync method, which is defined as a leak API. For a small size code, there are little data needing to be saved. But if the code becoming large, the data flow facts and path edges will grow exponentially. To find which data structure consumes memory mainly, we count the memory usage of 3 data structures path edge, incoming, and end summary. According to our experiments, pass edge consumes most of memory. Incoming and end summary consume most of the rest of memory. According to the finding above, we designed our two-disk droid to improve the scalability of IFDS framework. Disk droid contains two parts optimization, hot edge selector and disk scheduler. We will introduce hot edge selector firstly. According to our experiments, we count the use times of each pass edge. We find that most of the pass edges are visited only once, and only less than 2% of the pass edges are visited more than 10 times. So most of pass edges can be discarded directly, and only a small part pass edges need to be saved in memory. So we design hot edge selector algorithm and change IFDS algorithm. If a pass edge is not a hot edge, we don't add it into pass edge to save memory. But it is difficult to distinguish whether a pass edge is hot edge or not. We defined three heuristics to determine whether a pass edge is hot or not. 1. N is a loop header. 2. N is a function entry, or N is an exit node with D related to the formal parameters of procedure of N, or N is a return site with D related to the actual parameters at the call site. 3. P is derived from a backward IFDS pass in FluDroid. The implement disk droid based on FluDroid, an IFDS-based taint analysis tool. We compared disk droid with hot edge selector optimization and FluDroid in terms of time and memory. The horizontal axis represents the benchmarks, and vertical axis represents performance and memory ration normalized to FluDroid. The black column represents time, and the gray column represents memory. The optimization is very effective for the 9 apps with memory usage reduced from 31.6% to 75.8%. However, the memory usage improvements are insignificant for the 6 benchmarks with a memory usage reduction of less than 16%. According to our algorithm, we will recalculate pass edges, which is discarded and reused, resulting in an increased number of computations. We count the computations of each benchmark and compare disk droid with FluDroid. The number of computations increases significantly, from 1.08 times to 3.33 times. The app CZP has the largest computational increase of 3.33 times. However, it still speeds up. This is because the target statement of not hot edges are monitor statement, if statement, switch statement, not statement usually. They can be computed very efficiently. Some apps cannot be analyzed under 10 GB memory budget, even though we apply hot edge selector. So we design disk scheduler implements a set of schemes to efficiently swap data in and out of memory, expand memory. The IFDS solver produces and saves pass edges in memory. When the memory reaches the threshold, disk scheduler selects partial pass edges swap out into disk. If IFDS solver reuses the pass edges in disk, disk scheduler selects and swaps these pass edges in memory. Which pass edge needs to be swapped out? The IFDS algorithm is a work list algorithm. IFDS solver produces and pushes pass edges into work list in order, and pops the pass edge in the head of work list to calculate and produce new pass edges, and then Pass edges at the front of the work list will be used soon, so disk scheduler will remain these pass edges in memory firstly. How to swap out? We design 5 grouping policies. 1. Method policy. Package pass edges which belong to the same method. 2. Method and source policy. Package pass edges which belong to the same method and with the same source fact. 3. Method and target policy. Package pass edges which belong to the same method and with the same target fact. 4. Source policy. Package pass edges with the same source fact. 5. Target policy. Package pass edges with the same target fact. We download 2,053 apps from F-Droid. 825 apps are not applicable since they either don't require IFDS solvers or cannot be processed by Suite's front end. 1,047 apps are small and can be analyzed by FluDroid with less than 10 GB of memory. We exclude these apps and evaluate the rest apps. In the rest apps, there are 19 apps taking 10 to 128 GB of memory to analyze, and FluDroid cannot analyze the other 162 apps under the memory budget of 128 GB. In the experiments, we limit the memory usage of DiskDroid to 10 GB and that of FluDroid to 128 GB. DiskDroid processes the same results as FluDroid validated by DroidBench and apps. We compare the performance of DiskDroid with default configure and FluDroid. DiskDroid outperforms FluDroid by averagely 8.6%, despite giving a much smaller memory budget. The performance differences of the two tools vary widely across the 19 benchmarks, from a large slowdown of 54.5% to a significant speedup of 58.1%. For 21 apps requiring more than 128 GB of RAM by FluDroid, DiskDroid can analyze each app in 3 hours. Method scheme cannot analyze most of benchmarks. We do not display it. For DKAA app, method and resource policy slow down more than 100%. Source scheme exhibits the best runtime performance, and it is used as the default grouping scheme. We compare the runtime performance of different swapping policies with an enforced swap ratio. Default is the policy in DiskDroid, and random is the policy to randomly swap out pass edge groups. The policy default 0% swaps out all inactive groups and keep all active groups in memory. The random policy performs poorly, with 112% slowdown over FluDroid for CGT, and it times out for the 5 apps. The default 0% policy also fails to analyze these 5 apps. Comparing default 50% to default 70%, the runtime differences are insignificant when a different swapping ratio is enforced. We present a disk-assisted approach to improve memory scalability of existing IFDS algorithms and develop DiskDroid, a new tent analysis tool based on disk-assisted IFDS solver. With 2 memory-oriented optimizations, DiskDroid can analyze apps requiring up to 128 GB of memory for FluDroid under the memory budget of 10 GB, with an overall performance improvement of 8.6%. DiskDroid is available publicly. Thanks for your time and patience. If you have any question, please contact us by the following email.